Hello students, welcome to the class of topological space. So when X is a non-empty set and tau is a topology on X, then the pair X tau is called topological space. We know this definition. Topological space, TS. Okay. Then members of this collection tau is called open sets in the topological space. I am going to define the open sets in a topological space. Then open sets in a topological space X tau are the members of tau. Since empty set and full set belongs to any topological space, they are always open with respect to any topology. Empty set and full set are always open, being a members in tau. Okay. Now, how will you compare two topologies on a set? Let X be a non-empty set. Okay. Tau 1 and tau 2 be two topologies on X. Two topologies on X. Then, how to compare tau 1 and tau 2? So, here the since tau 1 and tau 2 are collection of subsets of capital X, the comparison will be by means of subsets, correct? So, when tau 1, the collection tau 1 is contained in tau 2, we say that tau 1 and tau 2 are comparable. Either tau 1 contained in tau 2 or tau 2 contained in tau 1. If tau 1 or tau 2 is contained in another one, then we will say tau 1 and tau 2 are comparable. Remember, the tau 1 and tau 2 should be topologies on the same set X. Comparable. Okay. And what is the meaning of tau 1 contained in tau 2? Tau 1 contained in tau 2 means every element of tau 1 is contained in tau 2. That means a set is open with respect to tau 1 is open with respect to tau 2. That is the meaning. That is all open sets in the topological space X tau 1 is contained in the topological space X tau 2. All open sets. Okay. It is a meaning of tau 1 contained in tau 2. Then we say that the topologies are comparable. Now, is it true that every topology can be comparable? No. Sometimes topologies cannot be compared even though they are defined in a same set. Okay, let's see some examples. For example, consider the set X is equal to element some A comma B, two element set. Okay, consider the topology tau 1 is empty set, full set, and the set is singleton A only, and tau 2 be empty set, full set, and the set B. Okay. Now, we already discussed that tau 1 and tau 2 are topologies on the set X, and these topologies tau 1 and tau 2 are called as Sierpinski topology. Both these topologies are called Sierpinski topology. Okay. And can you say that tau 1 is contained in tau 2 or tau 2 is contained in tau 1? If tau 1 is contained in tau 2, all the elements in tau 1 should be contained in tau 2. Here empty set and full set are belongs to both of them. But singleton A not contained in tau 2 or singleton B not contained in tau 1. Correct? So here tau 1 and tau 2 cannot be comparable. Not comparable. So, there exist topologies which are not comparable. Okay. Now, for the comparable topology, we consider some example. X is equal to ABC and take topology tau as empty set, full set, set AB. Okay, and this is some tau 1 and tau 2 equal to set X and empty. Actually this tau 2 is the indiscrete topology, correct? Then clearly tau I is contained in tau 1. Tau I is contained in tau 1. I make some little difference. Here I take tau 1 equal to empty set, full set AB, comma, set A, comma, set B. Okay, little bigger. Then tau I is clearly contained in tau 1, correct? Okay, and tau 2 be a topology empty set, full set and singleton A itself. Okay, then you can see that all the members of tau 2, empty set, full set and singleton A, all are belongs to tau 1 also. So that tau 2 clearly contained in tau 1. So that tau 2 and tau 1 are comparable topologies. Tau I and tau 1 are comparable topologies. Okay, so here tau 2 and tau 1 are comparable. Simplice, tau 2 and tau 1 are comparable topologies. Okay, now let X be any set, X be any non-empty set. Okay, then you can compare topologies on X with the indiscrete and discrete topology always. Tau I and tau D be indiscrete and discrete topologies, indiscrete and discrete topologies respectively. Then any topology, any other topology on X can be always comparable with the discrete and indiscrete topology. Since if tau is a topology on X, then tau I will be contained in tau, which is contained in tau D, because tau D is the largest topology and tau I is the smallest topology for any other topology, correct? So which implies tau will be comparable with the tau I and tau will be compared with the tau D. Okay, any topology can be compared with the tau I and tau D always. Okay, so there exist comparable as well as non-comparable topologies on a same set. Now for an example, you consider real line with the usual topology. This is a topological space, and you consider real line with the semi-open interval topology. I defined as tau RS, right closed sets. Okay, then which one is stronger topology? What is a stronger topology? Stronger means when tau 1 contained in tau 2, we say that tau 2 is a stronger topology than tau 1, or tau 1 is a weaker topology than tau 2. That is a kind of some comparison. Okay, here we consider real line with the usual topology and real line with the semi-open interval topology. Okay, what is tau u? Tau u is collection of all A such that for every A in A, there exists R greater than 0 such that interval of the form A minus R, A plus R completely contained in A. And what is tau RS? Right closed sets, collection of all A such that for every A in A, the same definition, there exists R greater than 0 such that interval of the form right closed A minus R comma closed A. Here it is open A minus R comma A closed contained in A. Okay, let's see which comparison is possible here. Okay, now let A be a member in collection tau u. Then what can you say about A is a subset of real line, and for every A in A, there exists R greater than 0 such that interval of the form A minus R, A plus R is contained in A. Okay, now to see the set A belongs to tau RS or not, we want for every A in A, there exists R greater than such that half open, right? Here now A is here in real line and this is some A minus R, A plus R. Now we have for every A in small a in capital A, there is a real number R greater than 0 such that interval A minus R to A plus R is completely contained in R, real line. Therefore, you can say the interval A minus R to closed A, this is also contained in R, right? So, which actually implies the interval A minus R comma A closed contained in A, because the full interval is contained in A, then of course the half interval is also contained in A, and closed A comma A plus are contained in A. Okay, this is true for every small a element of capital A. So what can you say that? Which implies this capital A satisfies the property of tau RS as well as tau LS. Lower semi-open interval topology and right closed semi-open interval topology. Correct? So which means that when you take an element in a usual topology, which implies that element also belongs to semi-open interval topologies. Correct? So tau u is contained in tau RS and tau u is actually contained in tau LS also. Lower limit, both of the lower limit topologies. Which implies, which is the stronger topology? Actually, semi-open interval topologies are stronger than usual topology, because any set which is open in tau u will be always open with respect to semi-open interval topology. Okay, which implies semi-open interval topologies are stronger than usual topology on real line. Clear? Now let's see what about the union of topologies and intersection of topology. Is it from a topology or not? We will see it. Okay, suppose let X be a non-empty set. For example, I take X is equal to A comma B. Okay, define tau 1 is equal to the Sierpinski topology X, empty set X and singleton A, and tau 2 B, tau 1 is tau 2 is equal to empty set X and singleton B. Okay, what is tau 1 union tau 2? Tau 1 union tau 2 equal to their union is empty set, full set and singleton A and singleton B. Clearly tau 1 and tau 2 are topologies. They are called Sierpinski topology. Sierpinski topology. Okay. What about tau 1 union tau 2? Is it a topology? You can see that tau 1 union tau 2 is not closed under union. Clearly, what is singleton A comma singleton B? They are belongs to tau 1 union tau 2. What about their union? Singleton A union singleton B equal to the set A comma B. Set A comma B. Oh, I would. Set A comma B also belongs to tau 1 union tau 2, right? So okay, I will give some variation in this example. Okay. A, B, comma C. Comma C. Okay. Then clearly tau 1 and tau 2 are topologies. Okay. Tau 1 union tau 2 equal to this one only. Clearly, what will happen now? A comma B. A comma B is a set not in tau 1 union tau 2. Correct? Otherwise, tau 1 union tau 2 will be equal to set AB. AB is capital X only. That's why I changed it into ABC. Okay. Not in tau 1 union tau 2. Which implies tau 1 union tau 2 is not closed under union. Union of its elements. Therefore, it is not a topology. So, you can note that union of topology need not be a topology. Union of topologies need not be a topology. Now, what about their intersection? Let's see. That is the result. Of course, intersection of topologies is a topology. So I will prove it as a theorem. Let X be a non-empty set and collection toi I in I be an indexed family of topologies on X if tau equal to intersection I in I toi. That means tau is the intersection of all topologies on X. Then tau is a topology. Tau is a topology on X, and tau is the least topology. Actually, tau is the weaker topology than each toi, and tau is the weaker topology. Than each toi, or each toi is stronger than tau. Okay, proof. To prove tau is a topology, we have to verify 4 axioms. What is tau? Intersection I in I toi, and each toi is a topology on X. Okay. Clearly, full set and empty set belongs to toi for every I. Why? Because each toi is a topology should contain empty set and full set, which implies empty set and full set will belongs to intersection I in I toi, which is equal to tau. So first 2 axioms can be verified easily. Now for the third axiom, tau is closed under arbitrary union. Okay, so I take collection A alpha belongs to tau, which implies each A alpha belongs to tau, which is equal to intersection I in I tau I. So every A alpha will be belongs to tau I for every I, correct? Which implies tau I belongs to, tau I A alpha belongs to tau I for every I equal to 1, 2, 3, etc. n. Not 1, 2, 3, etc. n, for every I, because here the collection is arbitrary. Since the collection is arbitrary, I can write for every I. Okay. Since each tau I is a topology, union alpha A alpha belongs to tau I for every I, which implies union alpha A alpha belongs to intersection I in I tau I, which implies union alpha A alpha belongs to tau. So tau is closed under arbitrary union. Similarly, we can prove that tau is closed under finite intersection. If A1, A2, etc. A and B finite number of sets belongs to tau, then these AIs are belongs to tau I for every I equal to 1, 2, 3, etc. n, which implies intersection I equal to 1 to n AI belongs to tau I for every I, which implies intersection I equal to 1 to n AI belongs to intersection I in I tau I, which means intersection I equal to 1 to n AI belongs to our tau. So tau is closed under finite intersection also. So intersection of all topologies form a topology which is a weaker topology than every tau I in this collection. So which means tau is a topology. Now what is tau? Tau is intersection I in I tau I, right? So every tau I will contains this topology, correct? Which implies tau is contained in tau I for every I. That's why tau is weaker and each tau I is stronger. Okay, every tau I is stronger than tau because tau I contains tau. Now let's see some example of a topology on real line. Okay, Consider our set X as real line. Consider the real line. Okay. And I define a topology tau on R such that which contains sets of the form A union B, where A is a member in usual topology of real line. Tau u, I represent it by tau u, okay. And what is B? B is a subset of any subset of irrationals R minus Q. Then tau is a topology on real line. Okay. Then tau is a topology because if A equal to empty set, then A will be belongs to usual topology because empty set always belongs to every topology. B also take B equal to empty. Then B belongs to, B is a subset of R minus Q is true. Correct? Then what will be A union B? A union B equal to empty union empty, that is empty set again. So empty set can be written as A union B, where A is empty which is belongs to tau u, and B is empty which is clearly a subset of R minus Q, which means empty set is a member belongs to this collection tau. And what about the full set? For that, take A equal to the real line. Then being a full set, A will be contained in tau u, correct? Yes. And take B equal to empty set. Then empty set is a subset of R minus Q is true. Then what is A union B? A union B equal to real line union empty, that is equal to real line. So real line can be written as A union B, or A equal to R, which is contained in, which is belongs to tau u, the usual topology. This is A, okay. And empty set is subset of R minus Q. So real line belongs to our collection tau is true. Okay. Now we have to verify arbitrary union and finite intersection. If you take a union of members in this collection, that is again is of the form A union B. Similarly as intersection. Therefore, clearly tau is closed under arbitrary union and finite intersection. Therefore, tau is a topology on real line. And you can see that, and in this topology, real line with tau is a topological space, correct? What is tau? Sets of the form A union B, where A is member in tau u and B is any subset of real irrationals. Okay. Now in this topology, it is seen that if B equal to empty is fixed, then what is A? A will be varying on, then A union B equal to A itself. What is A? A is a member in tau u, correct? Then what are the sets A union B, which are nothing but elements from tau u, correct? Therefore, for every A in tau u, A will be belongs to tau, correct? Therefore, tau u will be contained in tau. So what can you say that? This topology tau is actually stronger than our usual topology. Our usual topology on real line, because in this topology all the sets which are open in usual topology are also belongs to this topology, because you take B equal to empty set, then A union B format will becomes elements in tau u only. Okay. Now also if A equal to empty, what will happen? If A equal to empty is fixed, then what is A union B? A union B is B itself. What is B? B is varying over irrationals, correct? A union B equal to B only. So tau contains, what is tau? In this case, tau will be collection of B such that B is a subset of R minus Q, right? So you can say that any subset of irrationals is open in this topology. So in this topology, what you can say, any subset of real line is open. Members of tau are called open sets. So when you fix A equal to empty, then B is nothing but the subsets of R minus Q. So every V will be belongs to tau. Therefore, every subset of irrationals are open in this topology. Every subset of R minus Q is open in this topology. Also, it has one more important property, that real line with this topology R tau is called scattered line. Real line with this topology is called scattered line. And this topology tau is called scattering topology on real line. Scattering topology on real line. Because every set of irrational numbers is open in this topology. So that will be scattered. What are irrational? Irrationals are scattered on real line. That's why this topology is called a scattered topology. Okay. Let's see one more example of topology in real line. Okay, consider real line. Tau is defined to be empty set, full set, and sets of the form interval a comma infinity, where A is varying over real line. This tau is a topology on real line because clearly empty set and full set belongs to tau. And what about their union? If you consider union of these kinds of sets, empty union R is R union a comma infinity is real line, and empty union a comma infinity, sets of the form a comma infinity is a comma infinity. Okay, so clearly tau is closed under their unions and intersection. What about their intersection? Their intersection, empty union R union a infinity is real line. Empty intersection R intersection a infinity is empty itself, and R union a infinity is real line. R intersection a infinity will be a infinity. So all of these elements are belongs to tau again. And what about their intersection? If the sets are of the form collection a comma infinity a in R, then their intersection a in R a comma infinity. We need only check finite intersection, right? Suppose union. Okay, let's check their union. Union a in R, sets of the form a comma infinity. This is nothing but real line again, and it belongs to our tau. So it is closed under arbitrary union is true. What about their finite intersection? When sets of the form only open interval a comma infinity, that is of the form some a1 infinity, a2 infinity, etc. This is some enumeration an infinity. Then their intersection I equal to 1 to n ai comma infinity will be become, it is of the form some b infinity, where what is b? B is the minimum of these ai's, a1 a2 etc. an. Okay, and this is also of the form b infinity, b in real number, so which is closed under finite intersection also. Therefore tau is a topology again. Now can you compare this topology with respect to with the usual topology on real line? What is usual topology? It consists of all the open intervals and their unions, correct? And clearly empty set and real line are belongs to tau u, and sets of the form a infinity. Is it belongs to our usual topology? Yes, since it is being an open interval, it is also belongs to our usual topology. So clearly empty set full set belongs to tau implies empty set full set belongs to tau u also, because usual topology contains all. Here x is real line, sorry. Okay, now sets of the form a infinity belongs to tau, correct? And is it belongs to tau u? Yes, of course, because tau u is a usual topology. Usual topology consists of all the open intervals of real line. Implies A infinity also belongs to tau u. So what can you say about all members of tau is also member of the usual topology, which means tau is contained in tau u, which means usual topology is stronger than this topology tau on real line. So we already know that semi-open interval topologies are stronger. Tau ls or tau rs are stronger than tau u. Now tau u is stronger than this topology tau. This is the comparison of these three topologies. Remember, tau ls and tau rs are not comparable. Okay.